We're going to talk in this section about parent graphs. Now, parent graphs in our section are going to refer to the 5 basic graphs that you need to have their general shape memorized. So some of them are up here with our lovely silly dancing men. Not all of them, and we're not going to do the circle, but I wanted to get all 5 on the same page so that you could copy this down into your notes. Okay, first important parent graph is the graph of the function y equals x squared. Y equals x squared is a parabola. The vertex is at 0, 0, and it looks something like that. You can get a more accurate graph by plotting points, making like an X and Y chart, but the point of graphing functions at this level is to get rough, but hopefully pretty accurate sketches of these, not perfect graphs. We would use computer programs for those anyway. Okay, the next graph that you need to know is y equals x cubed. My dear friend calls this the disco function. So y equals x cubed also goes through 0, 0, but it does like a John Travolta move. Cool. Okay, rough sketch of y equals x cubed. Let's see, next graph. Y equals the absolute value of x. This is our victory graph up here. It makes a V. It's kind of like the V version of a parabola. So there's a rough sketch of our V graph, our absolute value graph. Let's see, what am I forgetting? Oh yeah, one of my favorites, the square root of x. So y equals the square root of x is really a parabola flipped over on its side, because y equals x squared and y equals the square root of x would be kind of what we would call inverse functions of each other. So it's flipped over on its side. And to me, this graph kind of looks like half of a rainbow. But it's the same as the graph x equals y squared. It's just the top half of it, where x equals y squared would be both the top and bottom half of that parabola. In y equals x squared, we only graph the positive portion. We only graph the top. Okay, the last graph probably is the one that you're the least familiar with if you have not yet had pre-calculus or college level algebra, and it's y equals 1 over x. Now, y equals 1 over x has an important domain restriction. And the top 3 graphs up here, y equals x squared, y equals x cubed, and y equals the absolute value of x, you'll notice if you've done the previous section on domain, these graphs, each of them, these functions have domain all real numbers. There are no square roots, there are no fractions. Their graphs extend to the far left and the far right, each one of them. Now they have limited ranges, but they definitely have all real numbers for the top 3 graphs for the domain. For y equals the square root of x, it has domain that x has to be greater than or equal to 0. And that's reflected in that is demonstrated in the graph. All of the x's are on the right-hand side of the y-axis, so they're all positive x's because we don't graph any imaginary numbers. Y equals 1 over x. Remember, the one thing that we can't do with fractions is we can't divide by 0. So x is not allowed to be equal to 0, which would be right here on top of the y-axis. So what we have here is an asymptote at x equals 0. Also, y will never be equal to 0. There is no value that would make 1 over x equal to a 0. So we have 2 asymptotes. An asymptote is a word you may have heard before. What an asymptote does is it acts kind of like a magnet. So it draws the graph closer and closer and closer to the line, but it doesn't actually have to touch that line. And in this case, neither this vertical asymptote nor this horizontal asymptote are crossed by the graph. So what we have kind of looks like back-to-back parabolas. That's what it looks like. They're actually not parabolas because they have asymptotes. A true parabola, does not have any asymptotes. These are hyperbolas. They resemble back-to-back parabolas, but they have asymptotes for each one of them. Okay, so make sure you have these 5 graphs in your notes. You're going to refer back to them from time to time in 3.4 and in 3.5. Now we're going to talk about graphing something called piecewise functions. And a piecewise function is really just part of an entire function. So on the left-hand side, just for the practice, we're going to graph y equals the absolute value of x. And like we talked about in the previous slide, y equals the absolute value of x looks like a v. Now on the right-hand side, if we were to graph the same graph, y equals the absolute value of x, but for only some x values, for x less than or equal to 2, negative 2, sorry, I might graph the whole graph, and then I erase everything except for this region here. So let's find x equals negative 2 would be here. Since it's less than without an equals to sign under it, I'm going to put an open dot. And for x is less than negative 2, that means we're to the left. So now I'm going to get my eraser and I'm going to erase all the other parts of my graph. So here we have the graph of what used to be the entire absolute value of f, like we have over here in blue, but now is just for a small piece of our function, just for the x's less than 2. So a piecewise function is just a piece of a graph that we've been working with. Now what's cool about these is once you chop this up into little pieces, you can add other graphs on there. So watch our next example. So here for the first example, we're going to graph y equals x cubed. And at the moment, I'm going to ignore the pieces that we're supposed to graph. So I'm just going to graph x cubed roughly like we had on the first screen of this video. Now I'm going to look at what piece I'm supposed to include, and then I'm going to erase everything else that I'm not supposed to have. So at x equals negative 1, you know it's a really good idea? It's a really good idea to take your starting point and ending point x values, plug them into your function, and figure out what ordered pairs they start and end at. So y equals negative 1 cubed would be negative 1. So here at x equals negative 1, y is negative 1. Since it's not equals to underneath, I have an open circle there. That's a negative 1. For the other point, y equals 2 cubed gives me 8. So I have the ordered pair negative 1, and 2, 8 as the starting point and ending point of this graph. So 1, 2, let's say this is 8. It is equal to here, so I'll have a closed dot at 8, and I want all the x's in, I only want the piece where the x's are in between these two values, so I only want this piece in here. So I'm going to get my eraser, and I'm going to erase everything else. So there's the graph of y equals x cubed, only with the piece between negative 1 and 2. Okay, so now here's one really cool thing that we can do. We can do, I'm going to move this down to give me a little bit more room here. So let's say for this example over here, I want to graph y equals the graph that we have, So x cubed between -1 and 2. But let's say I want to put another graph over here where I have room. So maybe I put in blue y equals x cubed when x is between -1 and 2. And let's do something nice and easy. Let's graph 3x when x is less than or equal to -1. So I'm graphing x cubed when x is between -1 and 2. So this graph right here. So again, it's nice to know my starting point and stopping point. When x is -1, x cubed is also -1. So I'm at -1, -1 with an open circle because there's no equals to. And it goes up to 2 and 8. So I would normally graph the whole x cubed. But because I'm only wanting to include a piece of it, I'm going to erase everything except a nice big fat closed dot there, except the piece that I'm looking for. Okay, now for the other graph, y equals, I'll go to my purple pen, 3x. Okay, so remember this is like y equals mx plus b. So my y-intercept is 0. I would go up 3 and over 1. So I would normally have a graph that would come in like this. Let me do this in one line. Oh, sorry, I can't draw a straight line. I'm really bad at that. Ooh, I can get out my ruler. This is pretty cool. Excuse me. Ruler. I wonder if you folks can see the ruler. So normally I would have that ruler there, or that line there. That's the graph of the line with the y-intercept of 0 and the slope of 3 over 1. But I only want a piece of it. I only want the piece when x is less than or equal to -1. So I really want to erase, okay, here at -1. It would be nice to know that starting point. Let's see, make my ruler go away. That would be 3 times -1 is -3. And since it's equals to, then I have a closed dot there, but I do want to erase my line. I need a much smaller eraser. There we go. A little more precise here. I want to erase my line. Oh, I erased my other graph too. Oops. There we go. So here's what we have, and I'm going to put just for emphasis, I'm going to put a little arrow here because it goes on forever. So when x is less than -1, we have the line, and when x is between -1 and 2, we have the cubic function. So one piece and another piece for a piecewise function. What I find troublesome about these is what I was doing here, where I graphed my line and then erasing. I find that annoying. So it's not a bad idea to graph the starting point and stopping point like I was doing here and here and here. Let's practice this with another problem. So for the first one, let's graph two functions. Y equals 2x minus 1 when x is less than 0, and y equals x squared when x is greater than 0. Okay, so let's see. Y equals 2x minus 1. So that is a line. It starts at -1 and goes up 2 and over 1. So I'll just graph that. It starts at -1, goes up 2 over 1. I'll get my ruler out again. I am super curious if you watching at home can see the ruler. Oh, come on, ruler. There we go. Pretty good. away. Cool. Okay, so there's the graph. Ooh, but I don't want the whole thing, right? I only want when x is less than 0 with an open circle. So here's 0. I only want this piece down here. So I'm going to get my eraser and I'm going to erase the rest of it. Erase. I have that really fine eraser now. There we go. Cool. And then on the other side, I have y equals x squared, which would normally be my parabola, but I only want a piece of it. I only want the piece when x is greater than or, oh, I forgot, didn't I? I forgot my open circle. Bad, bad, bad. Let's see. There we go. And I'll go back to my blue pen. That's not really blue, but that's okay. Do my open circle. Okay. So here's y equals x squared, and I want only the piece when x is greater than or equal to 0. So here's x is 0. The big greater than or equal to 0 is on the right. So I'm going to get my eraser. Maybe I'll make it a little bit bigger now. And I'll erase everything to the left as well as I can. And maybe for emphasis, just put a big fat dot right there. Cool. So when x is less than 0, I have the line 2x minus 1. But when x is greater than 0, I have the parabola. One question I get frequently when we do this section is, why? Why do we graph these? Why do we learn piecewise functions? So I have a short example of when you would have a piecewise function in just everyday life. Forget biology or calculus. You would have a piecewise function. Over the summer, I had visitors at my house. And this summer there was the hot set of days where it was like 107, 111 was the highest it got here in Loomis. And we got charged a different rate prior to when we were using our air conditioner a lot. When we started using, our energy use went up, we started using a lot more energy. Our rate was at a totally different, our charges were calculated at a totally different rate. So if we kept our energy use less than some kilowatt hours, then we were charged a nicer rate. But if we went over that threshold, then they increased how they calculated our charges. So there were two different ways of calculating our total rate depending on how much energy we were using. So PG&E using, or SMUD, or whoever you have, they use piecewise functions to calculate how much they charge you. Okay, let's do an example, another example. There we go. Let's graph y equals the piecewise function. So they've got these brace just to show that y is both of these. When x's are less than or equal to 0, our graph is going to look like the absolute value. And when x is greater than or 0, our graph is going to look like this line. Okay, so let's start with the first one. Absolute value graph looks like that, or V. But now I want to erase all the portions less than or equal to 0. So that would be everything over here. And since it's equal to, put a nice big fat closed circle, and I'll erase all the other stuff. There we go. Okay, now the other portion, y equals negative 3x plus 4. So wrong way. 1, 2, 3, 4. But I want to go down 1, 2, 3, and over 1. So I'd like to graph, I should get my line. This line, but I only want a part of that, and let's look at what part we want. We want just the part when x's are bigger than or equal to 0, so that would be here. I'm sorry, greater than 0 with not equals to. So I need to have, when I'm doing my erasing, and I erase all the others, I need to erase in here and give myself an open circle because that's the one that is not equal to. Cool. Okay, let's practice one more and then we'll be done. Cool. This f of x graph consists of 3 pieces. The line 3x plus 4 when x is less than or equal to 0, the square root of x when x is between 0 and 4, and just 2 when x is greater than 4. Cool, so let's graph this. So let's do the line first just because it comes on the top. So 3x plus 4, so 1, 2, 3, 4. I'm going to go up 3 over 1. I like you using this ruler. This is kind of nice. There we go. There's our line. Okay. But I want to erase the part I don't need. So this line, I only want the piece here. X's are less than or equal to 0. So that would be a nice fat dot at 4 because it's equal to, and erase everything else. I needed it. I personally needed it so I can see what the line looks like. I am not good about just graphing the piece from step 1. I kind of need to see the whole thing. Okay, and then let's do the square root. So square root of x looks like this. But I only want the piece where x is between 0 and 4. It's not equal to at 0, so I need to put in a nice open circle there. And at x equals 4, okay, little math here. At x equals 4, the square root of x is the square root of 4, which is 2. So we're at 4, 2. So 1, 2, 3, 4. Sort of. You should be at... That's a terrible graph, Mary Beth. That's supposed to be it too. How about I'm going to fix my square root just a little bit. It's a little flatter than what I drew. Let's go. That's better. That's a better square root graph. So there we go. Okay, and then I only want the x's between those two. Okay, and then x equals 2. Remember, that's a horizontal line. At x equals 2, oh, that's weird. X equals 2 is this spot right here also. So it's technically supposed to be an open circle at x equals 2. It just coincidentally was a closed circle anyway from the purple graph, from the square root of 4 that's equal to 2. So sometimes your open circles get filled in if the two graphs that are adjoining happen to have the same y value at their starting point and ending point. Cool. Okay, so there's 3 pieces to that graph. And this right here is our horizontal line, f of x equals 2 or y equals 2.